wormholes, and time travel, science or science fiction. Introduction. Hello, and welcome, friends. Tonight, we're about to step into one of the strangest, most thrilling questions humanity has ever asked. Is time travel really possible? And could wormholes be the key to unlocking it? If you grew up in the 1980s or 90s, chances are you've seen time travel on the big screen. Maybe you remember Marty McFly racing through time in Back to the Future, or the unstoppable cyborg in The Terminator. Maybe you were blown away by the cosmic wormhole in Interstellar, designed with real physics in mind. But here's the amazing part. These aren't just wild movie ideas. Behind the science fiction, there are real equations, written by the greatest minds of physics: Albert Einstein, Kip Thorne, and Stephen Hawking, that suggest time travel and wormholes might just be possible. In this journey, we'll explore the science of wormholes and relativity, the mystery of paradoxes and alternate timelines, the danger of what could go wrong, and the imagination that drives both scientists and storytellers. By the end, we'll try to answer the big question: is time travel a scientific reality waiting to happen, or will it remain forever in the realm of science fiction? So, grab a coffee, settle in, and get ready, because for the next 50 minutes, we're going to bend time, fold space, and take a ride through the universe like no other. The dream of time travel. Human beings have always been fascinated by the idea of escaping the limits of time. We live our lives in one direction, from past to present to future. We grow older, we remember yesterday, and we imagine tomorrow. But what if we could break free from that straight line? If you look back at ancient stories, you'll find surprising tales of time travel. In Hindu mythology, King Kakudmi travels to meet the god Brahma. He believes only a short time has passed, but when he returns, countless generations have gone by on Earth. In Japanese folklore, there's the tale of Urashima Tar, a fisherman who visits an undersea palace. When he comes back home, centuries have passed. These stories show us something important. People, across cultures and centuries, dreamed about time moving differently, long before science gave us the language to describe it. Fast forward to the 19th century, and the imagination took a leap. In 1895, H.G. Wells published The Time Machine. Unlike magical stories, Wells approached time travel with a scientific twist. He suggested time was a dimension, just like length, width, and height. If we could move through those, why not through time as well? His novel didn't just entertain, it planted the seed that maybe, just maybe, time travel could be possible. Then came the real game changer, Albert Einstein. In the early 20th century, Einstein shattered our simple view of time as universal and unchanging. His theory of relativity showed that time is flexibly bends, stretches, and slows down depending on speed and gravity. Suddenly, the dream of time travel was no longer just myth or fiction. It had scientific teeth. Think about it. If time can stretch and bend, then in theory, we might find ways to slip through it, just like stepping off the sidewalk and taking a shortcut through an alley. This was the moment when humanity's dream of time travel crossed from legend into the realm of science. Einstein's universe and the possibility of wormholes. Einstein didn't just change physics, rewrote our entire understanding of reality. Before him, people thought space and time were separate. Time ticked the same for everyone, everywhere, like a giant universal clock. But Einstein showed that wasn't true at all. He introduced the idea of spacetime, a single fabric that weaves space and time together. Imagine stretching out a rubber sheet. Now, place a heavy bowling ball in the middle. The ball sinks into the sheet, curving it. That's exactly how stars and planets bend space-time. The greater the mass, the deeper the curve. And what we feel as gravity is just objects following those curves down. Here's where it gets really interesting. If space and time are connected, then bending space also bends time. travel near something massive like a black hole and time itself slows down compared to faraway observers. In 1935, Einstein and his colleague Nathan Rosen discovered something remarkable while working on his equations. They realized that, mathematically, two different regions of spacetime could be connected by a bridge. This became known as the Einstein-Rosen bridge, or, as we like to call it, a wormhole. Picture this. You have a piece of paper. On one corner, you draw point A. On the opposite corner, you draw point B. The long way across the page is like normal space travel. But if you fold the paper so the 2 points touch, then poke a hole through, suddenly A and B are connected by a shortcut. That hole is your wormhole. Sounds like science fiction, maybe, but Einstein's equations say it's possible. The catch: wormholes collapse almost instantly. They're unstable, snapping shut faster than light. To keep one open, you'd need something called exotic matter, bizarre form of matter with negative energy density. Normal matter can't do the job. We've never observed exotic matter in large amounts, but quantum physics hints it might exist in tiny flashes deep in the quantum foam of the universe. If one day we learn how to harness it, we might not just open a wormhole, might keep it open long enough to step through. And here's the wild part. If wormholes exist, they could do more than connect 2 points in space. They might also connect to points in time. That means, in theory, a wormhole could be both a cosmic shortcut and a time machine. How time travel could work now that we know wormholes are at least possible in Einstein's math. Let's ask the big question. How exactly could time travel work? There are 3 main scientific pathways that physicists take seriously, each stranger than the last. Time dilation, traveling to the future. Einstein's theory of relativity tells us that time doesn't flow the same everywhere. It depends on speed and gravity. Here's an example. Imagine 2 twins. One stays on Earth, the other boards a spaceship and travels close to the speed of light. For the traveling twin, time slows down. A few years might pass on the ship, but decades could pass on Earth. This isn't science fiction. It's been proven with atomic clocks flown on jets and satellites. The time difference is tiny in those experiments, but at near light speed, the effect becomes enormous. In theory, if you flew fast enough, you could leap hundreds or even thousands of years into the future. So yes, time travel to the future is scientifically real, but only in one direction. Wormholes, shortcuts through time. Now, what about traveling backwards? That's where wormholes come in. Remember, if you move one end of a wormhole at near light speed, or place it near a strong gravitational field, time at that end runs slower than at the other. Step through, and you could come out not only in a different place, but in a different time. For example, imagine a wormhole with one end near Earth, and the other end on a spaceship moving close to light speed. Years pass differently at each end. Walk through, and you might step out decades in the past or the future. It sounds wild, but it's consistent with relativity. The problem: we'd need that exotic matter to stabilize the wormhole. Without it, the tunnel collapses before you can even blink. 3. Cosmic strings, hypothetical time loops. Another exotic idea comes from cosmic strings, theoretical objects that may have formed after the Big Bang. Think of them as extremely thin, dense threads of space-time stretching across the universe. If 2 cosmic strings passed by each other at near light speed, the distortion of space-time could, in theory, create closed time loops. Step inside such a loop, and you might circle back into your own past. We've never seen cosmic strings, but the math doesn't rule them out. So, in summary, traveling into the future, that's real, just need faster ships. Traveling into the past, possible in theory, but dependent on wormholes or exotic cosmic structures. The science is just. But before we start packing our bags for a trip to ancient Rome or the year 3000, we have to face something troubling. Time travel paradoxes. Paradoxes of time travel. Chapter: Paradoxes of time travel. So far, The science says time travel could be possible. But here's the problem. The moment you start thinking about traveling to the past, logic itself begins to break down. Physicists call these puzzles time travel, paradoxes, strange contradictions that could make the whole idea impossible. Let's explore the most famous ones. The grandfather paradox. Imagine you build a time machine, travel back in time, and accidentally or intentionally stop your grandfather from meeting your grandmother. If that happens, your parents are never born, which means you are never born. But if you were never born, how did you go back to stop him in the first place? It's a logical loop that has no consistent answer. That's the grandfather paradox. Time travel, creating events that undo themselves. The bootstrap paradox. This one is even stranger. Suppose you go back in time and hand Shakespeare a copy of Hamlet. He publishes it, and the play becomes famous. Centuries later, you read it in school, travel back in time, and give it to Shakespeare again. So who actually wrote Hamlet? You, Shakespeare? Or did the play just exist in an endless loop with no true origin? That's the bootstrap paradox. When something is created out of nothing, a self-contained time loop. The multiple timelines theory. Some scientists try to solve these paradoxes by suggesting that time isn't a single, fixed river. Instead, every time you change something in the past, you create a new branch of reality. Go back and prevent your grandfather from meeting your grandmother, and you don't erase yourself. Instead, you shift into a parallel timeline where you were never born. Your original timeline still exists, but you can't go back to it. This is sometimes called the many worlds interpretation, and it's been popular in science fiction. Think of movies like Avengers, Endgame, or TV shows like Loki, where every change spins off into a new universe. The chronology protection conjecture. One of the greatest minds of modern physics, Stephen Hawking, didn't believe time travel to the past was possible at all. He proposed something called the chronology protection conjecture. His idea was simple. The laws of physics will always prevent paradoxes from happening. In other words, if you try to create a paradox, something will stop you. Maybe the wormhole collapses. Maybe radiation fries your time machine. Maybe you're just unable to change the past. Nature, in a sense, protects the timeline. So where does that leave us? Time travel to the future. No paradoxes there, since you're just moving forward faster than everyone else. But traveling to the past is messy, confusing, and possibly forbidden by the very structure of reality. Still, paradoxes haven't stopped writers, filmmakers, and scientists from dreaming. If anything, they make the idea of time travel even more fascinating. After all, the best puzzles are the ones we don't have answers to. Yet, the chronology protection conjecture, one of the greatest minds of modern physics, Stephen Hawking, didn't believe time travel to the past was possible at all. He proposed something called the chronology protection conjecture. His idea was simple. The laws of physics will always prevent paradoxes from happening. In other words, if you try to create a paradox, something will stop you. Maybe the wormhole collapses. Maybe radiation fries your time machine. Maybe you're just unable to change the past. Nature, in a sense, protects the timeline. So where does that leave us? Time travel to the future. No paradoxes there, since you're just moving forward faster than everyone else. But traveling to the past is messy, confusing, and possibly forbidden by the very structure of reality. Still, paradoxes haven't stopped writers, filmmakers, and scientists from dreaming. If anything, they make the idea of time travel even more fascinating. After all, the best puzzles are the ones we don't have answers to. Yet, the chronology protection conjecture, one of the greatest minds of modern physics, Stephen Hawking, didn't believe time travel to the past was possible at all. He proposed something called the chronology protection conjecture. His idea was simple. The laws of physics will always prevent paradoxes from happening. In other words, if you try to create a paradox, Something will stop you. Maybe the wormhole collapses. Maybe radiation fries your time machine. Maybe you're just unable to change the past. Nature, in a sense, protects the timeline. So where does that leave us? Time travel to the future, no paradoxes there, since you're just moving forward faster than everyone else. But traveling to the past is messy, confusing, and possibly forbidden by the very structure of reality. Still, paradoxes haven't stopped writers, filmmakers, and scientists from dreaming. If anything, they make the idea of time travel even more fascinating. After all, the best puzzles are the ones we don't have answers to. Yet wormholes in science fiction versus science fiction. Wormholes capture our imagination so powerfully. It's because we've seen them again and again in science fiction. Movies, TV shows, and novels love wormholes because they make the impossibly instant travel across space and time look easy. But how do those fictional versions stack up against real science? Wormholes in popular culture. In Interstellar 2014, the crew uses a wormhole near Saturn to reach another galaxy. What made this film special was that physicist Kip Thorne, a real Nobel Prize winner, helped design the visuals. The glowing sphere we see on screen is one of the most scientifically accurate depictions of a wormhole ever shown. In Stargate, wormholes are like portals. Step through a ring, and you're instantly on another world. It's cinematic and exciting, but simplified compared to what equations suggest in the Marvel Universe. Wormholes often appear as swirling tunnels of light, giant cosmic highways through space. And in Star Trek, wormholes serve as shortcuts though often with unpredictable dangers. These portrayals inspire us, but they also bend the rules for storytelling. What real science says physicists think wormholes wouldn't look like tunnels at all. Instead, they'd appear as a sphere or bubble of distorted space. Imagine a shimmering ball hanging in space. From the outside, it would look like a doorway where light bends and twists, showing glimpses of whatever lies on the other side. If you entered, the experience might be disorienting. The laws of physics could behave strangely, gravity pulling in unexpected directions, light scattering in ways our brains can't fully process, and the risks, immense. The walls of a wormhole could collapse instantly. The tidal forces might stretch and tear objects apart. Radiation trapped inside could be deadly, unlike the smooth rides we see in films. The real trip through a wormhole, if it's even possible, could be violent and dangerous. Why fiction still matters even if movies exaggerate. They serve a purpose. They inspire curiosity. Many scientists today admit they were first captivated by wormholes, not in a textbook, but in a film or novel. Science fiction plants the seed. Science then asks, what if? So while the silver screen shows us glowing tunnels and easy shortcuts, the reality is stranger, harsher, and far more complex. And maybe that makes it even more exciting. Could wormholes actually exist? So far, wormholes sound like an exciting idea, but are they really out there in the universe, waiting to be found? Or are they just mathematical curiosities that exist only on paper? Have we found any? The short answer is no. We haven't observed a wormhole directly. Astronomers have searched the skies for strange objects that might act like wormholes, but so far, nothing conclusive has been found. However, wormholes might look a lot like black holes. Both bend light, both warp space-time, and both are invisible, except for the way they affect their surroundings. Some scientists have even suggested that if we saw a black hole behaving in an unusual way, like letting matter escape from the other side, it could actually be a wormhole in disguise. Quantum wormholes, the tiny possibility here's where it gets even stranger. On the smallest scales of reality, in the world of quantum mechanics, space-time might not be smooth at all. Instead, it could be frothy and chaotic, full of tiny fluctuations. Some physicists believe that microscopic wormholes, called quantum wormholes, might be constantly appearing and disappearing in this quantum foam. They'd be unimaginably small, far smaller than an atom. But if we could ever learn to stabilize or inflate one, In theory, we might create a usable wormhole. The exotic matter problem, of course. All this runs into one giant roadblock: stability. A wormhole would collapse instantly unless it was held open by exotic matter with negative energy. Ordinary matter, like the stuff you and I are made of, won't work. We've detected small hints of negative energy in quantum experiments, like the Casimir effect, where empty space between two plates behaves oddly. But that's a microscopic effect, nowhere near enough to hold open a cosmic tunnel. So for now, exotic matter is more of a hope than a reality. So, could they exist? The truth is this: wormholes are not forbidden by the laws of physics. Einstein's equations allow them. Quantum physics teases at their possibility. But until we have evidence or a way to generate exotic matter, they remain hypothetical. Still, history teaches us something important. Black holes were once thought to be purely theoretical, just strange math scribbled on paper. Today, we've taken pictures of them. Maybe wormholes will follow the same path. The dangers of time travel *. We've explored how time travel might work, and how wormholes could be the key. But let's pause for a moment and ask, even if we could do it, should we? Because time travel isn't just a scientific challenge, it's also incredibly dangerous. Radiation hazards. Wormholes would create extreme conditions. As particles and light rush into them, intense radiation would build up. Anyone, or anything, trying to pass through could be bombarded with deadly energy. Even a perfectly built time machine might be lethal before the trip even begins. Spaghettification and tidal forces, just like near a black hole. The gravitational forces inside a wormhole might not pull evenly. Instead, one end of your body could be stretched while the other is compressed, a process scientists colorfully call spaghettification. Not exactly the smooth ride Hollywood promises. Causality violations. This is the biggest danger, not to your body, but to reality itself. If someone managed to travel into the past, they could disrupt the chain of cause and effect. Change one tiny event, and history could unravel. Imagine someone preventing a major invention, or worse, using time travel as a weapon. Think about it. Controlling time would be more powerful than any nuclear arsenal. You wouldn't need bombs if you could erase your enemy's entire history. That's why many physicists believe nature itself has built-in safeguards to prevent this kind of chaos. The chronology police. Hawking's warning. Stephen Hawking jokingly suggested that the universe has a kind of chronology police, laws of physics, that step in to stop time machines from working. His famous chronology protection conjecture basically says, the universe won't let you mess with time. In other words, if you try to build a time machine, something will always go wrong. Your wormhole collapses. Your exotic matter disappears, or your calculations fail. Not because you made a mistake, but because reality doesn't allow paradoxes. The bottom line: even if we had the technology, time travel might be too risky to attempt. The dangers aren't just physical, they're cosmic. We're talking about forces that could break not only but the very fabric of reality itself. Philosophical and human impacts. So far, we've looked at the science, the math, the physics, and the dangers of time travel. But let's step back and think about something deeper. What would it actually mean for humanity if time travel became real? Meeting the past. Imagine being able to step back in time and meet your younger self. What would you say? What advice would you give? Would you resist the temptation to change mistakes, or would you try to rewrite your life? Now imagine millions of people doing this. Historians visiting ancient Rome. Fans flocking to watch the Beatles in concert. Tourists snapping selfies at the signing of the Declaration of Independence. The past would no longer be a mystery, it would be a tourist destination. But what happens to history when too many people step into it? Does it lose its meaning? Does it remain history at all? Visiting the future on the other side. What if we could peek ahead, see our children's children, or glimpse the rise and fall of civilizations? Would, knowing the future, inspire us to improve it, or would it paralyze us with fear? There's also the question of power. If some governments or corporations controlled time travel, they could shape the future to their advantage. Entire economies, wars, even cultures could be rewritten. The human temptation at its core. Time travel appeals to something deeply human, regret. Who hasn't wished for a chance to go back and fix something, say the right words, make the right choice, prevent a tragedy? But maybe that's also the danger. If we lived in a world where every mistake could be undone, would we ever learn, grow, or take responsibility for our choices? Ethical questions. Time travel forces us to ask hard questions. Should the past be off limits, like a protected heritage site? If someone prevents a disaster, are they a hero or a criminal for changing history? If you met your future self, would that knowledge help you or destroy you? These aren't just scientific questions. They're moral, philosophical, and deeply personal. The bigger picture maybe. In the end, the greatest value of wormholes and time travel isn't in building machines, it's in how they make us think. They remind us that time is precious, that our choices matter, and that our brief journey through the present is something to treasure. Perhaps the real gift of time travel is not the ability to change the past or see the future, but to inspire us to live more fully in the now. After all this talk of wormholes, paradoxes, and cosmic shortcuts, where do we really stand? The truth is both exciting and humbling. Science says wormholes and time travel are possible in theory. Einstein's equations don't forbid them, and quantum physics hints they might exist on the tiniest scales. Reality says we don't have the technology, the exotic matter, or the stability to make them real, at least not yet. For now, wormholes remain a bridge between imagination and physics, a doorway that exists more in equations and stories than in the night sky. Time travel, meanwhile, lives in that strange space between what is mathematically allowed and what is practically impossible. But here's the beautiful part. 100 years ago, black holes were impossible. Today, we've photographed one. A century ago, space travel was pure science fiction. Today, humans live on the International Space Station, and private rockets fly to orbit every week. So maybe, just maybe, our great-grandchildren will look back at us the way we look back at Jules Verne or H.G. Wells. Maybe. One day, stepping through a wormhole won't be a dream, but an adventure. Until then, wormholes and time travel remind us of something essential. The universe is bigger, stranger, and more mysterious than we can imagine. And that mystery is what keeps us exploring. Thank you for joining me on this journey beyond space and time. If you enjoyed this exploration, don't forget to like, share, and subscribe for more adventures into the wonders of science and the cosmos.